So let's talk about balancing a redox reaction using the half reaction method. So this was also in your notes packet that you got in class, or if you are copying, this is a very common chart in almost every chemistry book. But the steps are, you first write the net ionic equation for the reaction, omitting spectator ions. Then you write the oxidation redox half reactions for the net ionic equation. You balance the atoms and charges in each half reaction. You adjust the coefficients so that the number of electrons lost in oxidation equals the number of electrons gained in reduction. Notice we multiply by a whole in the example, not just the number of electrons. And then we add the balanced half reactions and return the spectator ions. Now, not as easy said as done because we have two options. We can have these happen in acidic solution, and we can have these happen in basic solutions. So realize that when we're talking about half reactions, the species that is oxidized, meaning the electrons were lost, when electrons are lost, they're going to be on the product side. So you'll have your species, and then on the product side, it'll have some charge, and then some number of electrons lost, depending on what the charge is. Like iron, if it's changing to an iron +3, +3 means that it lost 3 electrons, so it's splitting off 3 electrons. Now the species that is reduced gains electrons as reactants. So you would have your species plus a certain number of electrons, whatever's needed to get it to that negative ion. Now O2 is sneaky because you have to realize each oxygen is going to be a -2. But because there's 2 over here, we'd have to have a coefficient of 2 because we're actually making 2 oxygen ions. And for 2 oxygen atoms to become 2 oxygen anions, each oxygen would need 2 electrons for a total of 4 electrons being gained to the oxygen molecule. It's a little simpler to see with hydrogen, so if we had 2 hydrogen protons and they were able to gain 2 electrons, then they could become a neutral hydrogen molecule. Now, another rules to add to your notes. Please remember we saw in the last video that in acidic solutions we can add water to fix an oxygen problem, and we can add hydrogen to fix a hydrogen problem. But when we're in basic solutions, we can only add OH negative, so hydroxide ions, to fix the oxygen problem. And we can add, whoops, that's wrong, H2O to fix the hydrogen problem that adding the OHs causes. So let's look at 2 lovely examples. First up, we are asked to use the half reaction method to balance this redox equation. And they've asked us to leave the balanced equation in full, lovely ionic form. So, if we follow our steps, this is to first write the net ionic equation for the reactions. Well, to be able to do that, you really have to figure out what your focus is. So what is being reduced and what is being oxidized. And you do that by looking at your oxidation numbers. So we start once again. So oxygen, this is not peroxide, so that's each oxygen is going to be a -2 times 4 is -8. So to have a -1 overall, this lovely creature is actually a +7. Again, -2 times 3 is -6. Each hydrogen is a +1, so that gives me +2. So if this is -6, +2, to get neutral, this sulfur has to be a +4. Now they tell us this Mn is a +2. Isn't that nice? Our oxygen is -2 times 4 would be a total of -8. Again, hydrogen's always a +1 pretty much. So we have this negative overall. So if we have -2 times 4 is -8, +1. To have a -1 overall, that means this sulfur must be a +6. That would be +7 plus -8 is -1 overall. And our water is not really involved. It's just kind of there. We'll deal with it later. but our H's and our O's aren't changing. Notice our H's are still the same, so we really don't care. O's are all the same, so we really don't care. What we care about is the sulfur and the manganese. So we notice manganese went from a positive 7 to a positive 2. Now to get from positive 7 way over here to a positive 2, I'm going towards the neutral. Neutral being 0. That means I am gaining electrons. I'm being less and less positive. This one has not that many electrons. This one has more electrons. Still more protons than electrons, but it had to gain 5 electrons to get from positive 7 to positive 2. So, if we remember oil rig, oxidation is lost, but reduction is gain. So I know that manganese is being reduced. So that should mean that sulfur is being oxidized. It is undergoing oxidation. So if I look from positive 4 to positive 6, it became more positive, meaning it lost electrons. Specifically, it lost 2. So if I look at my half reactions, okay, well I have my MnO4 species, and it's going to this Mn2 plus. Okay. Now remember, since it was being reduced, we saw in our example half equations that the species that is being reduced, it's going to have the electrons on the reactant side because the electrons are being added. So we already discussed how for this manganese, one manganese, to get all the way to being a manganese plus 2, it had to gain 5 electrons. Whew, that's a lot. But we have this lovely oxygen problem. But I personally deal with oxygens at the end, so let's continue with our electrons. So, we look at the next piece. So the next piece was this H2SO3 species, and it became this HSO4 negative 1 species, and the sulfur changed, and we already decided that to go from positive 4 to positive 6, that this particular sulfur had to lose 2 electrons. So my 2 electrons will be over here. But notice, we have a problem. We have a rather not so lovely problem, because we have to get our electrons to be balanced. We have to have a common multiple. And the closest common multiple between 5 and 2 is going to be 10. So that means I need to multiply this equation by 5, so that this will be 10 electrons. And I need to multiply this equation by 2, so it'll be 10 electrons. So I'm going to rewrite this because it's just easier. Organization is the key to passing this portion. And notice the 2 distributes. And then I'll rewrite this one. So now I have 5 H2SO3 would break and give me 5 HSO4 plus 10 electrons. Okay. So now we can see, ooh, our electrons are good. Okay. So nothing else divides out at the current moment. So when I add this all back together, I have 2 MnO4 negatives plus 5 H2SO3 yields 2 Mn2 plus 5 HSO4 negatives. Well, we have to do step 5 and balance the half reactions. Check. And return the spectator ions. Now, they already told us one of our spectators was the water. And this is an acidic solution. So, we know we're definitely going to have some water. And notice, we have 5 times 4 is 20 oxygens over here. But over here we have 8 plus 15 . So that's 23 oxygens. But I only have 20 over here. So that means I need 3 H2Os to fix my oxygens. Because we're an acid, we add water to fix our oxygen problems. But then I need to check my hydrogens. You see, I've got 6 here and 5 for a grand total of 11 hydrogen. Well, here I've got 10, but 10 is not 11. And you're probably thinking, oh no! But remember, we're in an acidic solution, so we can just add 1 extra little hydrogen ion and we should be balanced. Let's double check. 1 plus 10 is 11 hydrogen. 5 plus 6 is 11 hydrogen. 2 manganese. 2 manganese. 8 plus 15 is 23. 5 times 4 is 20. Plus 3 is 23 O's. We've got 5 sulfur. 5 sulfur. Everything's balanced. Everything's good. We have just used the half equation method to fully balance this lovely redox equation. So let's look at one that's in a base. So we start all over again. We start by looking at those oxidation numbers so we can decide who's being oxidized and who's being reduced. So we have our -2 oxygen, because you know oxygen rocks. And if it's a -2 and there's 2 of them, that's total -4. So that means this nitrogen is actually a +4. Okay? Well, if this is a +1, this is a -2. Because oxygen is always, pretty much always a -2. And oxygen is more electronegative than hydrogen. And this will give us our overall -1. So we have the -2. But notice, this is -2 times 2, -4. This is a -1 overall. So this nitrogen, though it looks like this one, it's not. This nitrogen is actually only a +3. Because -2 times 2 would give me -4. -4 plus +3 is -1. Rewind that if you missed that math. So when I look at this one, we have -2 times 3 is -6. So if we have a negative overall, this particular nitrogen is -5. Plus our water. And some of you are going, oh no! We've got oxygens all being the same, so we don't care. And, well, the hydrogen over here is in water, so it's still +1, so we don't care about it either. We have this one little nitrogen changing 2 different ways. And that's okay. This one is particularly good to be done with the half reaction method. So you chill out, take a chill pill, and you start thinking. Okay, so we have some of this NO2. We're obviously going to have rather large coefficient. Look at all those ends. Is becoming the NO2 negative. And some of this NO2 is becoming the NO3 negative. So now we have to look at what's actually happening within these 2 areas. So when the nitrogen is going this way, it's going from +4 to a +3. It's becoming less positive, meaning it gained an electron. 1 electron specifically. If it gained the electron, that means it is being reduced. Reduction is gain. The rig portion of our oil rig. So that means that 1 little electron is over here. But when the nitrogen is going to this species, from +4 to +5, That means it lost an additional electron. Please remember that oxidation is lost. So the electron is getting spit out over here. It's one little electron. Now, we see an oxygen problem in here. But we'll check it out in a minute. But notice, this one doesn't require any multiplication. The electrons are good. So when I add these together, notice this is 1, 2 of these things, so I have 2 NO2. And then I have my NO2 negative plus my NO3 negative. And they tell me I'm going to have some water. I believe them, but we'll check in a second. Now notice, we have 4 oxygen over here. But on the right, we've got 2 plus 3. That's 5. So that means I have an oxygen problem. And we said that when we're in a basic solution, that to fix the oxygen problem, we add OH. So since we don't have enough oxygen on this side, we have 4, and we need 5. Well, it means on this side, I'm going to have to add an OH. But when I add an OH, see, the problem is when I try to fix the H, I fix the H's by adding 2. Which means I have to refix my H. But does that mess up my oxygens? Well, let's look. 2 and 3 and 1 is a grand total of 6 oxygen. So if I have 2 times 2 is 4 oxygen. Plus these 2 oxygen. That's 6 O's. And I've got 2 H's, 2 H's, 2 N, 1, 2 N. It's good! You have completely balanced this lovely equation that was in a basic solution.